In this podcast, I want to talk about SAD, entrance and exit dose. This is going to be similar to the SSD, but the physical dose calculation is quite a bit different. With SSD, the isocenter is set to the skin surface at usually at a nominal 100 SSD. As the dose falls off and it goes down deeper into the patient, the percent depth dose has an inverse square component in it. So that's why you don't need to do a separate inverse square component as part of the calculation unless you're at a different SSD than the calibrated SSD. However, with SAD technique, it's different because TMR, TPR, TAR, they don't have that inverse square component factored into it because it's relative. It's relative at two different depths with the same source to axis distance. So it's only the attenuation that's being taken into account. So with this particular case, you'll notice, if you remember from week 2 with the SSD entrance and exit dose podcast, and I would encourage you to go back and watch it, our isodose lines look fairly similar. I have a max dose point again at 316. So before I was at 309. My 100% or my 100 centigrade line, travels all the way through the patient's body. This is instead of a 100 centimeter SSD, you can see my SSD is roughly 90 centimeters. So the thickness of my rando phantom is 20. My calc point is midplane, mid-depth, midline, mid-depth. So I'm 10 centimeters deep, a millimeter off. So I get a 90 centimeter SSD. This is my source to axis distance. So now this is a cleaner setup for the therapist to treat. Instead of turning the patient over, or instead of rotating the gantry around and setting a posterior SSD of 100 with mechanical manipulation of the couch or patient, instead I set isocenter center of the patient. Patient stays in the exact same spot. The couch doesn't have to move, and then the gantry just rotates around the patient with the isocenter midline. Much cleaner. The dosimetry works out similar. I have similar isodose lines, except you'll notice that my monitor units are slightly different. They're less. That makes sense because my source is closer to the patient, because my SSD is 10 centimeters shorter. So I'm going to have less monitor units, and we'll see that in just a second with the MU calculation. In fact, let's do that right now. So I have a data table for 6x, and this time instead of percent depth doses, I have tissue maximum ratios. So before, this was my percent depth dose table. If you remember from week 2, I have 10 centimeters field size, and then my 10 centimeter depth. My percent depth dose is 66.4. If I go to my tissue maximum ratio tables, I have a 10 centimeter field size here, and then my tissue max ratio, my TMR, at 10 centimeters is 0.774. So I get a different depth component. Again, up top here I have an inverse square factor. So for an SAD setup, I have to have an inverse square factor in there that accounts for the source to calibration distance divided by the source to calculation point distance squared is going to be my inverse square factor. Okay, I've kept the geometry simple for this plan. I have a 10 by 10 field size. I'm at a 10 centimeter depth, 6x, no wedges, no off axis, nothing fancy. So if I take 200 centigrade, my prescription to that point, divided by 0.774, which is my TMR, I get 258.4 MU. However, I also have that inverse square factor component. Divided by 1.03 is my standard inverse square for calculation to isocenter, because my inverse square factor is source to calibration distance 101.5 divided by source to calculation point distance 100, and I take that squared and I get 1.03. So my calculated monitor units are 200 divided by 0.774 times 1.03 is 251, and the computer told me 253, and that probably has to do with some of the missing scatter in the slope surface, from the phantom surface. That's fine. It's within a couple percent. So 253 monitor units is what I've calculated. It's less than my standard SSD setup. because I'm closer to the source. Now what do I want to do for entrance dose? How do I figure out entrance dose? Well, with my percent depth dose example from week 2, we had PDD equals dose at depth divided by dose at D max. And this is fine. We could use that. I have TMR for this week is dose at depth divided by dose at D max. And that's fine. We can do this. We can do this. So TMR, dose at depth, dose at D max equals dose at depth divided by the TMR. Well, what does that give us? Dose at depth is 200 centigrade to my calculation point. My TMR was 0.774. Okay. 200 divided by 0.774. Well, we do this and we get 258. Well, let's see what our dose is. Let me measure D max. Get my little dose pointer here. And it's roughly, it's 310. So what's going on? 310. I calculated 258 and they're saying 310. What am I missing? Well, the TMR component, the TMR doesn't have an inverse square component to it like the percent depth dose does, so we have to account for the inverse square law. This point is physically closer to the source in space than my point of calculation. So I have to have an inverse square factor component with this. So this gave me 258 centigrade, okay, but I need an inverse square component. So my inverse square component is going to be the distance to what's my distance to my original dose of 200 centigrade? That distance is 100 centimeters. What's my distance to D max? Well, my distance to D max is 100 centimeters was to ISO. My phantom is 20 centimeters thick, so I've got 10 centimeter depth. Okay, so then what's the distance from the source to D max? Well, it's 91.5, right? I figure I'm 90 centimeters SSD, and then I have an additional 1.5 centimeter depth to D max. And I need to take this squared. Okay, so if I take 100 divided by 91.5 and I square it, I get 1.194. Now, my dose at D max is equal to 258 centigrade, which I calculated from before, times my inverse square factor of 1.194. Gives me 308. Let's see what I get. 310. 311. So 1% different. So that's how we calculate entrance dose for SAD setup. Now, if you remember from week 2 on the SSD setup and exit dose, there's either the 2-step method or the 1-step method. It's the same concept, except we're using tissue maximum ratios instead of percent depth dose. And then you also have to factor in an inverse square component, because on the opposite side for the exit dose, this point is going to be further from the source. So not only do I have an additional 8.5 centimeters of attenuation relative to the calc point, but I'm also further from the source given a set of monitor units. And I'll let you try and do the exit dose inverse square factor and see if you come up with something close to 124 centigrade.